Well, thank you very much to the organizers for inviting me, and I think to Nash, who is responsible for suggesting me to the organizers, including himself, I guess. I'm really happy to be here to have a chance to share some of this research and to connect with this community of scholars. Today, I changed my title slightly. I'm still working on the terminology or what are the right words to apply to the concepts that I'll be talking about here. So the working version that probably changed like last night is now sharing solutions versus sharing perspectives. So we'll see if that resonates with the audience and can adapt it if it doesn't. So what I'm going to be talking about is this sort of idea of collective intelligence or wisdom of crowds. And in particular, I want to focus on applications of this to problem solving as opposed to predictive tasks. So I've worked on, in the past, some things about forecasting or making predictions where we're really trying to just come up with a number from a group of people who have their own opinions about a number. But now we're looking at a kind of more complex situation where we're trying to find the best possible solution to some kind of problem. And so to give a few examples of the kind of situations we'll be looking at, so one example, this is a mathematician over at UCLA named Terry Tao, who is often sort of described as like the best mathematician in the world right now. And not that long ago, back in 2015, he solved a problem called the Erdős discrepancy problem. This problem had been open for 80 years. It was a problem not open for 80 years because no one was thinking about it. It was just considered to be a very difficult open problem in mathematics. And the solution to this problem actually came partially through crowdsourcing. There's a project called the Polymath Project where they post a problem and they invite mathematicians all over the world to work on it. And what happened in the very end is that somebody was reading this and looking at Terry Tao's blog where he was talking about this problem, and they made a comment on there that said, based on where you are on the solution right now, you might think about this other problem that this seems similar to. And Terry Tao said, when he describes how this happened, he initially thought, that doesn't really make any sense. But then after he thought about it a little bit, he said, wow, maybe there is a connection there. And actually, within 2 weeks after that comment, the problem was solved. Okay. Other situations where we might think about applying this kind of modeling that I'm going to be discussing or be in healthcare, you might imagine that you come into the ER or you're in the hospital for some other reason, you're presenting with some symptoms. They start off with maybe, if you have symptoms of your stomach, it might be a gastroenterologist who sees you or whoever, a specialist in that area. But if they're not sort of able to fully solve that problem, or come up with a diagnosis that they're confident in, they may call in another specialist from another area, like a cardiologist or and so forth, and that person may come in, they have a discussion, and the cardiologist says, well, these are some possible diagnoses that I might think might be leading to this based on my expertise, but looking at the problem as you've described it to me so far. And then if they can't solve the problem there, they might bring in a third person and so on and so forth. Or similarly, like in an engineering team, you're going to have different people who have different specialties who all work together to produce some kind of a product, which is their best solution to whatever kind of problem they're trying to solve by selling this item. So when we think about what makes for sort of a wise crowd or a successful crowd, there are a couple of different dimensions that we might think about looking at and that have been looked at before in the literature. And a couple that I want to focus on today are team composition. So who is in the crowd? And in this area, we typically can think about, so this was supposed to represent diversity. I Googled diversity and clicked on images, and this is what kind of came up. And so
the bird's name there is magic.
Yes. And so, right, don't forget this chameleon on the tail. So the two kind of like key, or a couple of key variables that we think of when we look at team composition are individual ability, how good are the problem solvers on their own, and then diversity, how different are they from one another. And we know mathematically, like when it comes to the forecasting problem, we can really like precisely write down how does individual ability and how does team diversity in terms of our forecasts translate into crowd performance, right? And then we can think about optimizing who is in the team by optimizing these different variables. When it comes to problem solving, things are more complicated, but we still have some mathematical results, like work of Scott Page's, that shows under certain conditions, diversity even matters more than individual ability when kind of deciding the composition of a team. And then the other variable we want to think about is the communication network. So how, given these different pieces of information or perspectives that the individuals in our team have, how are they sharing those with one another? So in particular, we might have a situation where sort of everybody's talking to everybody and everyone has full access to all the information and all the opinions of all their collaborators, all the way down to a network that looks like this, where sort of there's kind of maximal distance between people, and we're really slowing down how fast information can spread from one person to another. So when we look at the results about in the literature on how communication networks matter, there are lots and lots of work on this, but I want to focus on really just two papers. The first one's by Lazar and Friedman in 2007 in Administrative Science Quarterly. They ran a bunch of simulation experiments with their agent-based models, basically, where they have, which I'll describe kind of the details more later. But the punchline that they take away from this is summed up in this quote, where they say that the more efficient a network was at disseminating information, the better the short-run performance, but the lower the long-run performance. So temporarily, it's good for having information to spread quickly, but in the long run, the teams performed better when you slowed information down by creating networks where people were basically far apart from each other. And the intuition behind this is, I think this is your question to Paul earlier, it's really a reframing of this old result by James March about exploration versus exploitation. So this is from March's paper from 1990, I don't have the date here, 1999? 1991, thanks. In which basically you have an organization that's comprised of individuals, and they can become socialized, they can learn from the organization, and the organization can learn from them. And that socialization rate tells you how fast they sort of conform to what he calls the organizational code, how fast they're socialized. And this is the average equilibrium knowledge at the end of the simulation. And what you see is that sort of the faster people learn, the worse off everybody is in terms of the performance of the organization. And this is exactly what Lazar and Friedman are also finding, that the faster that people communicate or faster that they share information in their simulations, the worse off the team does. And I'll explain in detail a little bit more the intuition, but it's really the same thing that's happening in the James March papers. And the reason I really want to delve into this is because there's an experimental paper by Winter Mason and Duncan Watts where they find the exact opposite with real-life people. Right? So they took people, I think these were college students, but maybe it was on Mechanical Turk. I can't remember. They were Turkers. OK, thanks. And they had them play this game where they were basically drilling for oil. And so the people were on the computer, and so they could control the network of who could talk to who and where they could see where the other people had drilled. They varied the network structure and looked at the performance of the teams. And what they found was the exact opposite, that efficient networks perform unambiguously better than inefficient networks. So the faster that people could communicate, the lower the average path length in these networks, the better the teams did. And so what we want to understand is why. Why is it that what's wrong in the Lazar and Friedman model, or is there something that at least is wrong for this situation that the experiment was performed in? So, so let's look at this is just a cartoon illustration of kind of the way that Lazar and Friedman went about their model. And then I'm going to take essentially their model and sort of ramp it up in one direction. We're going to add a dial to it. And so what they do, the way that they conceptualize problem solving and the way that lots of computational models of problem solving, whether it's of individuals or teams, proceed is that we think of solving a problem as trying to optimize some function. Right? And so typically this is a function over multiple different parameters. And so you think that each of these, just for simplicity, I'm going to have one parameter here. We can think of each point on this horizontal axis as a potential solution to the problem. And then the value of this function is how good that solution is to the problem, right? Agents are searching trying to optimize this function, right? If the agents did as good as possible, they would find that this solution over here is the best solution there is possible to this problem. But we think that agents don't know this total landscape, right? So they can't just automatically go to this optimal solution. So if we have two individuals, we'll call them A and B, are represented by these dots. This might be the current solution that person A is exploring, and this is the current solution that person B is exploring. And so we think like they sort of go to this solution and they maybe build a prototype of that model. Or if they're looking for drug discovery, they run a clinical trial of that drug and find out how well does it work. And so once they know that, then they proceed from there to search nearby for other better solutions. So we imagine that they have kind of local knowledge of the landscape, but they don't know the big picture. And so what can happen here, if we imagine that like each of these two agents, A and B, searched on their own, right, then agent A would say, well, here I am, and it looks like things are getting better if I move this direction, which could be, if I ramp up how much of chemical A I have in my drug compound, or if we think about like a marketing problem, like designing an advertisement, maybe this is like add more sex to it or whatever, or something, right? What's going to make this thing work better? And so they would, over time, move in this direction, and they might converge to this local optimum here, A star. And person B, on the other hand, might converge to this local optimum, B star. Now, if you think about how communication might impact this, though, now let's imagine that person A and person B can talk to one another. Right? So if we go back to before they've sort of converged here, if right at this point, person A and person B talk, and we say, here's the solution I've come up with, it's this good, and person B says, here's the solution I've come up, it's better, person A might say, well, your solution's better than mine, I'm going to come over to where you are, and together they would both converge to this point, B star. On the other hand, if they wait, if they both sort of independently operate and find the best solution they can, and they communicate later, right, after they've converged to these 2 points, then they would actually find out that this person A's point is actually better than person B. So you can see why there's this advantage to not communicating so quickly, because if you communicate so quickly, you might copy someone who's currently better than you, but who ultimately will be worse. Right? And in fact, if you think through it, like there's actually no advantage to communicating quickly except in the short run, if this is your framework. If what you do is you just copy someone who's better than you when you talk. Right? It's always better. I mean, there's no good. In the long run, you might as well all first optimize, because in this model, you can never converge to anything except for an individual's local optimum. There's nothing else you can do because everybody's using the same strategy of just hill climbing. And so the best thing you could do is converge to the best local optimum that any one person could get at from their starting point. And so after you kind of think through that, you realize like, oh yeah, well, no wonder that it would be better to communicate more slowly in this model. But if you think about this for a second now, this is really the essence of the Lazar and Friedman paper. This is how their model works. They have a more complicated landscape than this, and they have big teams of like hundreds of agents, and they're in more complicated networks. But it all comes down to this fact that if you just communicate slower, you get to find out if there are better local optima. So if we think about what we know, though, about the wisdom of crowds, this is not really the way we typically think about it. I mean, in terms of the real benefits of it. Because what this is all about here is sort of like bringing the floor of your team up to the ceiling. All that happens in this case is that the best possible performance you get is the performance of the best individual in your team. You never get like the synergy or where the team does better than the people that are in it in a model like this. Yes?
So why would we qualify this as a disadvantage of communication? It's more a disadvantage of the action taken after communication, which is to copy.
Yeah.
Instead, somebody could have said that the derivative at A is much sharper than a derivative at B. So even though while A is lesser than B, they might want to explore A more.
Yeah, that's a great point. Yes, absolutely. And so you're right, and that's what we're going to do, basically. I mean, we're not going to do that, but we're going to do the idea of that, which is to change how we communicate. Not change that we communicate, but what we share. So in this model, right, the best performance you get is the performance of your best individual. You never get better than anybody that's in the team, which goes against sort of everything we think about from, say, these popular press books like The Wisdom of Crowds, which is really all about how, together teams you can take a bunch of people who sort of don't know that much, and as a team they can know a lot, right? Or same thing with Scott Page's book, The Difference. You can take a bunch of sort of problem solvers who are not that great as individuals, but as a group they can perform better than even a group consisting of the best individuals, right? So this is all about that the team does better than the individuals that are in it, which is not at all what you see in the Lazar and Friedman paper. And so to kind of resolve the paradox of these results and try to understand how we can create a computational model that gives us a sort of richer theory along the lines of what you're saying of how team collaboration works, we're going to add a kind of extra dimension into this model, which I'm going to call communication quality. Okay? And so, in particular, we're going to imagine that agents might not just communicate my solution. I might not just say, this is the current solution I have, and then I say, well, that's better. Why don't I come over there? Instead, which is what we have so far in the Lazar and Friedman framework, we can imagine that agents can also share what we call perspectives. Okay? And so we can say that the agents are going to have different ways of searching the landscape, essentially, or different solutions that they can view it. I'll make this precise in a minute. And I can ask you, I can say to you, if you were in my shoes, if this was the solution you were considering, what would you do now? Okay? And so to give an example of this, and this is just kind of a nice time for me to thank my collaborators at the same time, I want to talk about the team of people that we put together for this grant. So Nash and Brian and Leslie, I can't find Nash or Leslie. There's Leslie, there she is. Nash disappeared. Are all here, and then also this is John Lang, the postdoc who's working with me on this project. All of us have different PhDs. Right? Nash is in communication, Leslie's in industrial organizational psychology, John's an applied mathematician, Brian's a sociologist, and was a pure mathematician originally. I don't know what I am now. And so, what is that?
An impure one.
Yeah, it's an impure mathematician, that's right, definitely. And so, what might happen, so we can imagine that if we were thinking about trying to solve a problem about how can we come up with a great model of team collaboration and problem solving, as that's the problem that we're working on, that's what the NIH gave us the money to try to solve, we could think, well, one possibility is we all sort of go off and we start building our own models and working on our own solutions, and then we get together, like at a conference like this, and we say, well, what have you come up with, Leslie? What have you come up with, Brian? What have you come up with, Nash? And then we all talk about it, and we say, well, Leslie's got the best model. Let's just go with hers. And so we all switch over, and that's what we do. That would be kind of what we see in the Lazar and Friedman framework. What we're talking about now is instead something like this. Like we're all working, and we're all kind of working on separate parts of the problem. And I come to this conference and I say, like right now, I talk about this is where I'm at so far. This is the model I've come up with. These are the results I have. And then Brian says to me, well, actually, there's some stuff from sociology that might be relevant to you. And like hearing what you're doing right now, like knowing what solution you're at, but looking at it from the perspective of a sociologist, here's what I see as a direction you might want to try. Like, why don't you add this into your model, or why don't you think about it this way? And then Leslie can say to me, given where you are, I see all the dials, and you've told me about the solution you're exploring right now, but as somebody who has a background in organizational psychology, you might want to think about this or go read these papers because they might push you in the right direction. And in fact, this like really happens. I was thinking about like the last time we met, exactly these processes happen. And then the same thing can happen. Brian can say, this is where I'm at so far. this is the data I have, this is what I'm thinking about, and then I can say, oh, did you think about trying X? Because, here's this mathematical fact you might not know about, like this certain measure of diversity or something that might be useful to you. And then we keep working, but we get to temporarily sort of borrow the brain of the other person who has a different way of seeing the problem than us. Right? So that's what we want to kind of try to instantiate in our computational model. And to emphasize, this is just one of my favorite examples of this that Scott Page introduced to me, just how much of a difference these different perspectives or different sort of ways of looking at a problem can make. I'm going to show you this quick game. All right, so this game's called Sum to 15. Herb Simon invented this game. How many of you already know how this works? Okay, great. Just Brian. Okay, good. So it's a very simple game. You lay out 9 cards on the table, numbered 1 to 9. It's a 2-player game. One person chosen at random to go first, and you take turns picking up cards. You pick up a card, I pick up a card, you pick up a card, I pick up a card. You keep going until one person somewhere in their hand has 3 cards that add up to 15. Okay? It doesn't have to be the first 3 cards. Anywhere in your hand, if you have a combination of 3 cards that add up to 15, you win. Whoever gets that first wins, and the game is over. It's possible to pick up all the cards and nobody has 15, in which case you tie. Okay? Does everybody kind of get how the game works? It's a simple game, but it's not actually super easy to think through how to play it. So is anybody up for playing this game with me? Just real quick. You want to give it a shot? Okay. So we'll play. What's your name?
Larry.
Larry. Thanks, Larry, for volunteering. So I'm going to, we'll put up here. So, and, you've never played this game, so don't feel bad if you lose. I'm really good at this game. And the one thing I want to ask everybody real quickly, though, is that because this is a thing about the wisdom of crowds, we all know, I only want to play this game against Larry. I don't want to play this game against the whole room, because it's going to be extremely tempting for you to yell out what Larry should do at some point, right? And if I play this game against the whole room, we'll just definitely tie, because there's no way that I can beat a whole room of scientists. And Larry, we may tie too. It's very possible. But we'll see. So here's the numbers. You feel confident you understand how the game works?
Yeah.
Okay, you want to go first? I like to keep track on my own paper too here. So you want to go first?
If I go first, I'll probably win.
You think so? Wow, okay. Go ahead. No, you might. Sometimes I make a mistake. Pick 5, okay. That's a good choice. All right, so Larry chooses 5. I'm going to go with 8. Okay. I'll take 7. I think we're going to tie. You're doing great. No, it's not impossible. You still have a chance to win.
Oh, I can pick.
You can keep going. Anywhere in your hand if you have 3.
Okay. Then 1.
Okay. Good. I think we're probably headed for a tie. Okay, so I'll take 9. Great. Okay, so we're about to tie. It doesn't matter at this point. So you took 2, and I'll take 4, and so you take 6, and we're done. Congratulations, Larry. You tied a world champion, sum to 15 player. Excellent. A round of applause for Larry. So, Larry, let me ask you. Would you rather play sum to 15 with me or tic-tac-toe? Which do you think you feel more confident about? That's usually an easier question.
Yeah, because I'm thinking there's too many traps in this one, not in that one.
Yeah, so most people find that they would rather play tic-tac-toe because if you know how to play tic-tac-toe very well, like you should never lose, right? Tic-tac-toe is a game where you should always tie unless you sort of make a blunder. Whereas sum to 15, it's like it's a little more complicated to think through what it is you're supposed to do. You have to kind of think all the time, like when you have 5 and 3, I have to think, okay, I have to sort of make sure that I block you from finishing it off. But at the same time, I'm trying to pick a number that might help me, so I'm playing offense and defense at the same time, and so forth. Well, if you think about it for a second, though, actually, sum to 15 and tic-tac-toe are the same game, right? And the reason why I am so good at sum to 15 is that while you were playing sum to 15, I was playing tic-tac-toe on my own paper. Every row, diagonal, and column in this magic square from second grade or whatever adds up to 15. And so getting 3 in a row, 3 numbers that add up to 15 is the same thing as getting 3 X's or 3 O's in a row in tic-tac-toe. And so what this illustrates is just how much having a different perspective can matter to solving a problem, right? When you see this game as sum to 15, it's very difficult to understand exactly what it is that you should do and what strategy you should be playing and how to win. Whereas if you see this game as tic-tac-toe, it's a fairly straightforward game, and it's much easier to know what to do. It's coming from this probably is similar in everybody's field, but I really think it was the case for me when I was back in pure mathematics, was that, some people think like, what does a pure mathematician do, especially my students? They're like, how could you possibly study, like, what is there to know still about math, right? It's a great question. But when you're working on my dissertation or something, it's not like I just have to do like more and more calculations and eventually I did the last calculation and then, okay, now the problem is done, right? What happens is like you work and work and work for a long time and you get basically nowhere. And then like you take a shower or you're walking the dog or you're at the beach or something, and all of a sudden you realize like, oh my gosh, if I saw the problem from this other direction, now the problem is much easier to solve. Just like Terry Tao found in the example at the beginning, right? It was like, oh my gosh, the error discrepancy problem is the same as this other problem, and that problem I can solve. Now I'm done. In 2 weeks, it's 80 years before that of like nobody getting anywhere, or getting somewhere but not making it all the way. And then in 2 weeks, once you've shifted your perspective to that direction, boom, it's done, right? And so we think about one of the ways that teams get this benefit of the different members is that they have different perspectives. And so I don't have to wait for that perspective to light up in my head. It can happen when we all get together, and then Leslie can say, have you thought about it from this perspective? And then I can say, whoa, now I can solve the problem. All of a sudden, this was like the last sort of piece of information that I needed to put this together. So that's what we want to do in our agent-based model. So I'm going to show you now the details of exactly what we did and some of our results. And I'll say that hopefully we're still in the semi-early stages of this, so I'm really excited to hear suggestions for what people would hope to do next. And ultimately, our goal with this as our team is to marry some of these computational approaches with some of the data that Nash and Brian and Leslie have and put it together to sort of really bring these two together in the long run. But we're not quite there yet. So everything we run, this is going to be our kind of like problem landscape. It's a 2-dimensional landscape. You can see that there's sort of like one big global max, like there's one really the best solution here, and then there's kind of a decent amount of noise and local optima. This problem landscape is quantitatively the same as the landscape used in the Mason and Watts experiments. Okay, so this is actually, we use the exact same math to generate this landscape. We also ran these experiments on NK landscapes that had the same structure as what the Lazar and Friedman paper used, so everything works the same. Doesn't really matter which landscape we use. But this is nice. NK landscapes have n dimensions, so they're really hard to show pictures of, whereas this is nice and 2-dimensional. This is a cross-section of the landscape running through the y equals 0.5 line. So it's just to give you an idea of sort of really how rough this surface is. So the way we're going to model these different perspectives or these different kind of specializations like sociology and psychology is as follows. You can imagine that, so there's a big lattice sort of laid out over this landscape of points that a person can test. These are possible solutions to our problem. So here's a person in the middle. This is the point, the current solution that they're considering. And so they can see or know the sort of goodness of these, 8 solutions that are nearest to them. So they can decide whether or not they want to move from where they are currently to one of these better solutions. And this is the standard, this is, if we were Lazar and Friedman, this is where we would stop in that paper. But what we do instead is we say, okay, but in addition to this, every agent has what we call like a specialization. They have their own special knowledge of a certain body of knowledge or type of solution to a problem. They're a sociologist, or they're a cardiologist, or whatever, in what case we're talking about. And that gives them access or knowledge of other solutions out there that aren't right where they are, but that match their specialization. So every solution in this space is labeled with a particular specialization, and as a specialist in that, I can see points that match my specialization a little bit further away than just right in my neighborhood. So for example, this person here is sort of the red specialization. So they can see all of these solutions as well. And they know how good those solutions are. And so now they have a few more choices. They don't have to just choose the best solution among these, but they can also see these other ones. And all the agents, so different agents have different specializations, which gives them access to different points. Okay, so you imagine like this is sort of all the different colors. And so what this means now is if I'm this person in red here, and this is my knowledge is all the red points out there, but I'm connected to someone who maybe has like a dark blue specialization, right? I can ask my dark blue friend, come over here. If you were where I am, that is, if you were building the solution that I have currently, what would you do? And they can say, well, from my knowledge, if I was doing what you're doing, I can see that actually there's some other points out here that are even better than the ones that you're thinking about. Why don't you try doing that? Right? And then now I get access to that knowledge from them, and I'm able to go try that point. Does this make sense as to what? Right? I only do this when I'm stuck. All right? So I keep working, and I'm happy working on my own until I get to a point where I can't make any further progress. And then I turn to my friends. And then I say to my friends, what would you do if you were where I am? And they can tell me, if I was where you are, these are the better solutions. These are the solutions. And if one of those is better, then I might try it. Yes?
Well, I think it seems to the assumption to imagine I'm the square. I can morph myself in the circle. But what if I just can't? Like you see me talking about, I see the better solution, but I'm limited by my disciplinary background. I will forever stay at the square. I cannot become a circle.
I can't, somehow I can't.
Yeah, I'm just imagining square and circle imagine different areas of expertise. I know that's a better solution, but it's a computer science. I can never morph myself into a computer scientist.
Yeah, so we don't have that in there now. I think one way we could do that is add another dial to this, which is sort of like a probability. Like maybe there's some distance between specializations that says, there's some specializations that are just too different from me that I can try them, or some probability that, even if you tell me that this is a good solution, there's only some probability that I'm able to move there. Yeah, that would be interesting to try. But we haven't. As it is now, if you tell me that that's a good thing to try, I can do it. Yeah.
Is it essential to this that that a solution's only offered when requested? For example, anyone who has a mother like mine knows that solutions are given unsolicited regularly, right? Is that a really important part of your point here?
That's a very good question. I don't know. I don't think it's going to be important, but because what's really going to constrain, so what is important is that you can only offer solutions to people you're connected to in the social network. You can only receive solutions from them. So that's really constraining how much sort of advice you could be getting. But whether or not those people offer you advice just all the time. That's basically going to kind of be speeding up communication. I don't think it's going to change the results, but yeah, it's another good thing to try. Yes?
I have a question similar to Connie's. So, I'm interested in diversity, the wisdom of the trials too, but when I look at the empirical data, I always want to say in the theoretical world that we should meet, but actually when different people try to talk to each other, I think one thing is maybe when they're too different, they cannot move due to the boundaries.
Mhm.
We may also find it difficult to communicate to each other.
Yes.
We cannot really understand what each other is talking about, or it takes too long to talk, or sometimes there's conflict. I just wonder if you can, include some probabilistics,
Yeah.
elements into that.
Absolutely, and like one of the big assumptions of this is that everybody, like the solutions that you know actually how good they are. This person in red knows how good all the red solutions are, and they can actually accurately say, that's a better solution, I'm going to move there. And then if my blue friend comes and tells me that these solutions are better, they can actually tell me exactly how good they are. And so I think another thing that we could think about as sort of another dial to add in here is some like uncertainty, and that could occur both at like, I can make errors in predicting how good a solution is, which might depend on how far away from me it is, and there could be an error in terms of communicating. Yeah, I think that would be really interesting too. But so far, we're kind of like best case scenario. I know exactly how good these solutions are, and I can tell you exactly how good they are, and you can just go ahead and implement them as well as you can. So we're going to think of having these sort of like two dials to our computational model here. One is the communication network. So these are what's the structure of people that you can talk to, right? And the results that I'm going to show you today, I'm going to take just sort of like the two extremes for the most part. I'm going to take a fully connected network where everybody can talk to everybody, and a linear network where you can only talk to the people to the left and right of you, or if you're at the end, you can only talk to one person, right? We've run this for a whole bunch of other networks. Like these are all the networks that were used in the Mason and Watts paper. We do that there too, and like you get sort of stuff that's in between, but I'm just going to show you the endpoints of the results for the most part. So that's going to be one dial. We're going to move from more connected to less connected networks. And then the other dial is going to be between this communication quality dial. So we're going to change the probability with which when I get stuck, if I turn to you, do you just tell me a solution? That is, tell me where you are and I copy it? Or do you share this perspective with me and give me a range of options based on what you could see, what you would do if you were in my shoes? So this is going to be a dial because it's a probability that this happens at any given time that I get stuck. Okay. So, and we'll see what happens. Okay. So when we share solutions, we just copy the better position. When we share perspectives, well, I think I've already described this, so we'll keep going. Okay, so here I'm going to walk through the results kind of step by step. The first thing here, so this is my communication quality dial down here. This is what percentage of the time, or what's the probability that I share a perspective versus just sharing a solution. That is just telling you where I'm at and you come over here. So when this is 0, this is the Lazar and Friedman model, where I just tell you, here's the solution I've got, and if it's better, you will move to me. Right? And as we ramp this up, more and more often, instead of sharing solutions, we're actually sharing perspectives. I'm coming to thinking about, if I was in your shoes, what would I do? So if we're all the way over here at 1, we're always sharing perspectives. So, and this line is for a completely fully connected network. We have 16 agents in this particular thing, and we run the model 1,000 times for every point. So this is an average of 1,000 simulations. And I'm showing you the performance of the best solution found by any member on the team. I'll show you the average performance of the team in a minute. But this is like, if we imagine at the very end, after working on our problem for a year or two, or however long we work on it, at the end we get together and we can say, okay, what is our best solution we found? What's the best chemical we found to treat this drug? Or what's the best advertising we come up with? This is what we got to. And so the first thing that you can see is that the more we share perspectives, the better we do, right? And we actually get now what we think of when we think about the wisdom of crowds, that the group up here is performing better than the individual agents in that group. When we're always sharing all these perspectives, we actually get something better than we are as individuals. Okay. Next one I want to show you now is this is what happens in a linear network. So this is the difference between these two lines is changing that communication network dial. So this is fast communication or lots of communication, and this is slow communication or very little communication among team members. So over here on the left, remember this where we're only sharing solutions. This is the Lazar and Friedman situation where they had in their paper, and we recover their result that slow communication outperforms fast communication, or low communication outperforms a lot of communication when you're just sharing solutions, when you're not really sharing problem-solving approaches. But as we ramp up how much we share these problem-solving approaches, right, once we get up to about 75%, right, now things have flipped, and it becomes better to communicate more, right? And in the end, over here, we get what we see in the Mason and Watts results, that it's the best performing teams are those that are communicating the most or in the most tightly connected networks. The next thing I'm going to show you now, this is the average performance of the teams. That is, if I look at the 16 people and take their average, and then I average that over 1,000 different simulations. So we see a couple of things that are different. So first of all, when you're sharing only solutions, the average performance and the best performance are basically the same. Because when you're sharing solutions, you're copying what other people are doing, and so everybody ends up doing the same thing at the end. And so your average and your best performing agent are all the same. But when you start sharing perspectives a lot, your average performance kind of takes this nosedive eventually. And what happens is, sort of as a team, the best member of the team is doing really well, but your average member in the team is not able to get those benefits because it's kind of like, Leslie comes over and tells me, here's what I would do if I was in your shoes, and then I can improve, but then Leslie goes back to working on whatever she was doing before, right? And so it may be, and that I go over and tell Leslie, this is what I would do if I was in your shoes, and she keeps going, but I stay where I'm at. I keep working on my own solution, and so I don't necessarily catch up. Maybe she's getting way, way, way off ahead of me, and every time she comes back and tells me, well, if I was in your shoes, this would be, she's helping me out, right? But I don't get to go all the way up to her level, even if she's way, way above me. And so this average performance drops down. Although the ordering is still the same, still, when we share solutions, only slow communication is better than fast communication. When we share perspectives, it's flipped. And where it flips is it flips even earlier, back here at like 30%. If we look at the average, it switches to being better to communicate more. Okay, so the next thing, so one of the things that this made us think about is like, well, that's great that when you share these perspectives, you do better as the best individual in the team, but this is kind of suggests that there might be some better combination. Like you don't want to just share perspectives, because as you can see, like what that results in is the average member of the team sort of falling behind. And so maybe there's some kind of like mix of communication that would be better, where I am at some point allowed, like after we work for a while and like I help Leslie out and she helps me out, and I help Brian out and Brian helps me out, and we both do well. But at some point we should say like, look, Leslie's so far ahead, let's just all go do what she's doing, right? And go from there. And so we looked at what happens if we share perspectives for a while, and then we switch to sharing solutions. We switch to kind of copying the best person. And this is what happens. So this is how long we keep sharing perspectives before we switch to sharing our solutions. So what we can see is that initially it's good to wait. This is kind of, again, like we think about it, we're slowing down the copying. If we think about what you're saying, this is like how long do we keep exploring before we start exploiting, right? Because copying someone else's better solutions is exploiting. We're saying your solution's better, we're going to go exploit what we know there. sharing perspectives is like allowing everybody to explore independently. And so what you see is like there's a benefit to waiting, to exploring for a while, but then those benefits kind of taper off, and this just stays basically constant forever after this point. At some point, it's really better to go ahead and switch to that exploitation mode. And when we do this, where we explore and then exploit, right, these dotted lines are the maximum performance from the previous graph. We can bring up the average performance of the whole group to the performance of the best agent, and sometimes we do even better than we did before, depending on the network structure. So this sort of suggests that like this is a good heuristic for a team to use. Like let's let everybody explore. We communicate, but we don't converge. We communicate, and I say this is how you should solve the problem, but I don't just take on your solution for a while, and then ultimately we switch to doing that. And then the last result that I want to show you really quickly is I'm going to sort of zoom in on the difference between these two endpoints. So what we see is that on this end, where people are only sharing solutions, right, this linear network does better than the fully connected network. So we're going to look at how this works as we move from a linear network to a fully connected network. And then over here, where the linear network does worse than the fully connected network, we're going to see how that transition happens. So that's what we're seeing right here. So this graph is for only sharing solutions, starting at a linear network and then adding edges to that network until we get to the fully connected network. This is like this is a zoomed in of just turning the connections dial, but keeping the communication quality fixed. So you can see that, like basically, this is another picture of Laser and Friedman's results. That as you add connections, when you just start copying solutions, your performance takes this nosedive. Right, the more communication you have, the worse that you do. But you see the exact opposite when we look at the other end of the graph, where you're talking about sharing perspectives, where you're talking about sharing the ways of solving a problem. As you ramp up this connections dial, you see a takeoff in performance, and so this more communication leads to better performance. And so this contrast really says that like there's this interaction between network structure or communication structure and communication quality as we've sort of defined it here. And so that's where I'll wrap up, and thank you for your attention.
I'm sure there are questions. Yes.
So there's work done on how do you learn in non-convex spaces, for example, simulated annealing, and more recent work on how do you put a convex manifold and explore. Let's talk about simulated annealing. It's kind of the same flavor as number of rounds that
yes.
heap is higher, then you slow down over time, and you try. So have you looked at that relationship?
So first of all, you're absolutely right. It's like, that's definitely the case. And we haven't like really applied that here. One of the things that we've thought about sort of separately is, still here, these are really simple agents. The individuals are like not very sophisticated. They just like see these points and then they move to a point that's better. Now they can just see more different points. And one of the things that we think, like if you look at what happened in the Mason and Watts experiment, people are smarter than this a little bit. Like they don't just they sort of explore, update they kind of have opinions about how good all the solutions are, and then they see like how good your solution is over here and how good's my solution over here, and they sort of think maybe they linearly interpolate or something like that. So I haven't thought about doing it with simulated annealing, but there's kind of like like this k-means classification. So we've thought about doing it that way, and we've got some mathematics for doing that, but we're still working on it. So that's a great idea. Yeah, Michael.
So just going back to the really interesting question that I forget who raised it earlier about adding an error. I think that if you add an error, you get an even stronger result, because if we're playing a game of, let's say it's to guess how much does PJ weigh, then we should all have secret ballot. And
Yes.
if we have secret ballot, our errors will cancel out and the law of large numbers will do its magic. But if we can see each other's votes as we're voting and change our vote when we see what others are voting, then the law of large numbers doesn't get to do its thing,
Right.
and we converge on a mistake. Whereas if what we share is not our guess of how much you weigh, but our algorithm that we use, like see how tall he is,
Yep.
and then look at this. If we share that, we protect ourselves from the invidious effects of non-independence on error correction with
Yep.
the law of large numbers.
Absolutely. Thanks. I think it's a good, that's a good, very good comment. I mean, and we could have a richer representation of like the individuals as sort of having these models basically, and sharing the variables that they.
Because the other way of thinking about the efficiency of the network is that efficient networks are really good at spreading the error.
Yes.
Especially if what convinces me that somebody else is right is the number of people who said the same thing, which is really the problem in guessing the weight of PJ or of a cow or whatever. You know, that when a lot of people say that number, that they have to be right. This many
Right.
people can't be wrong. You put that in and
Or forecasting who's going to win the
so
presidential
these
election.
efficient networks get really nasty.
Yeah. Yeah, that's a great suggestion.
In the matrix that had all the various colors, you had in the center the red square, and they were limited to the red square. So the person in the center had only those immediately adjacent to them that they would know about. Then you put up one in which there were other colored squares around, this one here. In Kaufman's early work with NK landscapes, this gets iterated every time so that the person in the middle will pick one of the 9 and move there.
Yeah.
And then in the next iteration, what that move does is it puts the person immediately adjacent to all those other choices that are not reds, that are different colors.
Yes,
Okay.
that is what happens here.
Yeah, that is what happens.
Yes, so once they move here, then all these become red. They can always see the points that are right next to them.
Okay.
No matter.
I thought you were saying that what happened was that they could reach out to any of the red spots, or maybe they had access to any of the green spots because they were connected by a network.
That is true too.
Oh,
So-
how can both be true?
So if I'm here
Uh-huh.
and I'm the red person, so if I'm working on my own, let's just say for a second, I get to choose to move to any of these spots or any of the red circles. As soon as I move there, like so I'll choose which of those is the best. And so if this is the best, once I move there, I now get access to all the local neighbors of where I am now. I can always see the solutions that are right next to me.
Yes.
And then I can also see any of these red circles that are sort of still within some wider radius, and I probably get access to some new red circles that are out further, because this is just a little chunk of the landscape here.
So this is a correlated landscape
Yes.
in Kaufman's term.
Yes.
Okay.
And right. And so, and if one of my green friends tells me, okay, move to there's a green square that's even better. If I move here, I get also access to the points right around that, and still I have access to the red points that are other red.
Linda, you
Yeah.
had a question. Yes, I'm curious if you've run hub and spoke networks, or if you think if you ran them, would they sort of amplify be more extreme of the linear, or be interested in your thoughts?
We haven't run exactly that. We did run a set of like Watt-Strogatz small world networks where we ramp up the rewiring, so that gives you a little bit of that flavor. And degree is really important for the sharing perspectives, because basically the more degree you have, the more perspectives you get, the better you do. So if we look at individual performance in these networks, the people who do the best are the people who have the highest degree. When we run these on the Watson-Strogatz networks, we can potentially have more variability in degree, or we run them on a bunch of Erdős-Rényi networks, and so you have more variability. people who have the highest degree do the best. It turns out that if you do this with Strogatz networks where you allow the degree to change, you can imagine there's kind of two different ways of randomizing networks. You could keep the degree, everybody having the same degree, but increase how random the ties are, or you could allow degree to change. I have a plot, so just have extra slides here. So this is what happens as you randomize edges, but you allow the degree to change. Both when you're only sharing solutions or sharing perspectives, it always hurts. And this is the average performance. I think actually if you looked at the best performance, you wouldn't see this. But what happens is that as you look at average performance when you're sharing perspectives, you get people who have very low degree, and so those people do badly. And so they pull down the average. I think the performance of the best, which I don't have a graph for sharing perspectives, will go up because you're going to get some people who have higher degree, and so they're going to do well. When you fix the degree and keep everybody's degree the same, this is really noisy. But basically, this is a very small scale. Basically, the performance when you share only perspectives doesn't really change. It doesn't actually matter if the connections are random or not random. And the intuition behind this is that when you perspectives actually don't diffuse. Because what happens, like if I ask Leslie for her psychologist's perspective for now and she gives me that information, I don't forever learn, I don't become a psychologist, and I don't then now have the ability to transfer my psychological knowledge to the next person over. I just get to use it temporarily, and then she goes back. And so because of that, the fact that these networks are more mixed up doesn't, it's actually, so in some sense talking about them in terms of efficiency is not really quite the right thing. It really has to do with degree when you're looking at only perspectives. Whereas efficiency really matters when you're only sharing solutions, because what happens is the solutions spread too fast and everybody converges too quickly. Yeah.
Well, thank you all for sharing your perspective and solutions.